Okay. Next is Newton-Raphson method, right. Gauss serial we have seen. Now, you see Newton-Raphson method, in short NR method, right. So, Newton-Raphson method also is an iterative method, and in your mathematics course you have studied Newton-Raphson method, right, solving that your what you call different problems, right. So, which approximate the set of nonlinear simultaneous equations to a set of linear equations, right, using Taylor series expansion, and the terms are restricted to first order approximation. We will only consider up to the Taylor series expansion only the first order terms, right. We will not go for second or higher order, right. So, for example, you take given a set of nonlinear equations. So, suppose it is given y 1 is equal to f 1, a function of x 1 x 2 up to x n. Similarly, y 2 is equal to f 2 x 1 x 2 up to x n. Similarly, up to y n is equal to f n x 1 x 2 up to x n. You take a set of nonlinear equation. So, this is equation 43. First we will see that iterative process, then we will go for load flow, right. So, this is your nonlinear equation. Now, just hold on. Now, suppose the initial estimate for the solution vector is given. These are the initial values given x 1 0, x 2 0 up to x n 0. For the all x values, initial values are given, right. Now, what you do, assuming delta x 1, delta x 2 up to delta x n, right, are the correction required for x 1 0, x 2 0, x n 0, right, respectively. Because every iteration you need to update the x values. So, these are the correction required, delta x 1, delta x 2, delta x n, right. So, that the equation 43, that means previous equation, that means this equation, this equation, equation 43, this equation, right. We can make it like this, that y 1 is equal to f 1, it is x 1 0 plus delta x 1, comma x 2 0 plus delta x 2, comma up to x n 0 plus delta x n, right. Because every you have to update this one, right. Similarly, y 2 is equal to f 2, x 1 0 plus delta x 1 plus x 2 0 plus delta x 2 up to x n 0 plus delta x n. For y n, f n, that x 1 0 plus delta x 1, x 2 0 plus delta x 2, x n 0 plus delta x n. This is equation 44, right. Now, this equation, when you put like this equation you have to expand in Taylor series, right, and we will consider only the first order this thing, your second order or higher derivatives will not consider, right. So, the equation of the set 44, because we have n number of nonlinear equation, can be extended by Taylor series for a function of 2 or more variables, right. For example, the following is obtained of the first equation of 44. I mean, if you take that first equation, that means this one, if just first equation you take, because it is set of nonlinear equations, right, consider only the your 44, then this one, sorry, this one, this first equation of the 44, this is 44, first equation of this one, right. So, if you do so, then you can write this y 1 is equal to f 1 x 1 0 plus delta x 1, x 2 0 plus delta x 2 up to x n 0 plus delta x, right. So, you expand it in Taylor series. So, it will become f 1 x 1 0 comma x 2 0 up to x n 0, then plus delta x 1 del f 1 upon del x 1, put that whatever I mean here you have to take the derivative and put the all initial values. That is why one your what we call a suffix 0 is shown here, right. That means del f 1 upon del x 1, whatever it comes you have to put that values, x values, right. Similarly, plus del x 2 del f 1 upon del x 2, same thing up to del x n del f 1 upon del x n plus psi 1 is the higher order term, so we will not consider, right. Whereas psi 1 is a function of higher powers of delta x 1, delta x 2 and delta x n, and second, third derivatives of the function f 1, and we will not consider that. We will take only up to this, right, only this term. So, this way first to expand in Taylor series, right. So, next is I will rotate this one. So, neglecting psi 1, the linear set of equation resulting is as follows. So, I will rotate this, right. So, that means y 1 is equal to, you can write f 1 x 1 0 comma x 2 0 up to x n 0 plus del x 1 del f 1 upon del x 1 plus del x n up to del f 1 upon del x n. This all these values actually del f 1 upon del x, you have to substitute the values of initial values and evaluate, that is why this was shown, right. So, similarly, y2 is equal to same thing f2 x10 x20 up to xn0 plus delta x1 del f2 upon del x1 up to del xn upon del f2 xn, right. So, similarly, that yn is equal to fn x10 x20 xn0 plus delta x1 del f upon del x1 up to up to plus delta xn del f upon del xn. This is equation 45, right. Now, you can write y1 minus f1 is equal to this one, y2 minus f2 is equal to this one, yn minus fn is equal to this one. So, same thing we are writing here, that y1 minus f1 x10 x20 up to xn0, then y2 minus f2 x10 x20 the function of all the initial values f2, then yn minus fn x10 x20 up to xn0 is equal to this from here this side, right. So, it is del f1 upon del x1, but all these things again and again not really understandable, that after take the derivative we have put that values, right, initial values, right, del f2 upon del f1 upon del x2. So, all the every iteration actually this matrix will change, right. So, anyway up to del f1 upon del xn, and similarly del f2 upon del x1, del f2 upon del x2, del f2 upon del xn. Here it is del fn upon del x1, del fn upon del x2, del fn upon del xn. This is delta x1, delta x2 up to delta xn, right. This equation is 46. This one, this mismatch, this one we let us define as a d, right, and this one, this one you define as a j, right. So, j actually is called the Jacobian for the function f I, right. Therefore, this equation if it is d and this is j and this residual vector delta x1 delta x2, this can be called as capital R, right, delta x1 delta x2 delta xn, this can be called as capital R, right. That means, d is equal to your can be written as jr, right. If this is d, this is j, and this vector if it is r, not shown here, but I am telling you, you can hear it, that delta x1 this can be r, then this one equation can be written as d is equal to jr. This is equation 47, right, where j is the Jacobian for the function f I and r is the change vector, that is delta x I, right. So, equation 47 may be written in iterative form, that is, suppose any iteration count your p, then dp is equal to jp into rp, p is the iteration count, right. So, that means, rp will be equal to jp inverse into dp, right. This is equation 48, right. So, the new values of xi's are calculated from I mean the xip plus 1 is equal to xip plus del xip, because rp is the vector, your del x1, del x2, del x3 up to del xn p. So, all if you know this one, that all del x can be computed, right, this one can be computed. So, this is rp is that your this thing actually r is like this, right, r is like this, del x1 del x2 this one, right. So, that's so all the del x value can be computed from equation 48, right. Therefore, this x can be updated, xip plus 1 is equal to xip, and from here you will get all delta x values. So, delta xip, this is equation 49, right. So, the process is repeated until two successive values for each xi differ only by specified tolerance, because you have to go for convergence characteristic, right. So, same way later we will see for Newton-Raphson method, and you have to see that solution has converged, right. So, in this process j can be evaluated in each iteration, may be evaluated only once provided del xi are changing slowly. If change in delta x is very small, then the change in the values of x will be very small. So, delta that is Jacobian matrix j, instead of evaluating in every iteration, very fast iteration you compute, after that retain it constant throughout the iterative process, right. So, because of quadratic convergence, Newton's method is mathematically superior to the Gauss-Seidel method. So, Newton-Raphson method is much superior than Gauss-Seidel method and is less prone to divergence with yield condition problem. So, if network is yield condition, then your what you call then Gauss seidel may fail to converge, right. So, what is yield conditioning? Later we will see. First, let us discuss about your what you call that Newton-Raphson method, right. So next that load flow using Newton-Raphson method. So, whatever little bit of mathematics we saw, that is your this thing. Now, load flow using your Newton-Raphson method, right. So, in this case your what you call more efficient and practical for large power systems, right. Main advantage of this method is that the number of iterations required to obtain a solution is independent of the size of the your problem, and computationally it is very fast here. So, basically what happens for Newton-Raphson method, that generally you will find it takes hardly 3 to 4 iterations to converge, even 2 to 3 iterations it converges, right. Whatever may be the dimension of the problem. Dimension of the problem means that number of bus bar. Suppose you consider 500 or 1000 bus bar problem, right. So, you will find number of iterations more or less are independent, right. So, what we are doing is now that rewriting equation 15 and 16, same equation we are rewriting, but numbering again 50 and 51 here, right. So, P I is equal to the power that your injected power at bus I, earlier we have derived this, k is equal to 1 to n V I V k y I k. So, hence onward I will not utter magnitude, because these are all magnitude bar it is there, cosine theta I k minus delta I plus delta k. So, and q I is equal to minus k is equal to 1 to n V I V k y I k sin theta I k minus delta I plus delta k. This is equation 51, right. So, it is a set of your what you call nonlinear equations, right. And but here also you have to consider P bus PQ bus and PV bus, right. So, equation 50 and 51, that means these two equations, right, that constitute a set of nonlinear algebraic equations in terms of independent variables. So, voltage magnitude in per unit and phase angles in radian, right. So, we can easily observe that two equations for each load bus is given by equation 50 and 51. That means, there are two equations for each load bus given P I and Q I for equation 50 and 51, right. So, and one equation for each voltage control bus given by equation 50, and if it is a PV bus, your voltage magnitude will remain constant, right. So, at the time P is known. So, one equation, right. So, given by equation 50. So, you have to now expand equation 50 and 51 in Taylor series and neglect higher order terms. That means, these equations, right, because all these things, right, we have to solve iteratively. So, and these are the nonlinear equation. Just now we saw that nonlinear equation how to expand it in Taylor series. So, P I and Q I you have to expand it in Taylor series, and you have to see that how things are happening, right. So, in this case what will happen, for this case also we will assume that bus 1 is a slack bus. So, we will see I is equal to 2 to n, right, bus 1 is a slack bus. So, in that case what will happen, that if you expand this thing and neglect higher terms in Taylor series, then your mathematical thing will be something like this, right. So, in this case, that if bus 1 is a slack bus and P is the iteration count, so it will be delta P 2 P, delta P 3 P up to delta P n P, this is P delta P part, then there is a mismatch, and delta Q 2 P, delta Q 3 P up to delta Q n P is equal to, right, look at this matrix, right. So, this is delta P 2 upon P, everywhere P means iteration count. So, I am not telling again and again P, but you can see it here everywhere P means iteration count. I will just tell this partial derivatives, delta P 2 upon delta delta 2, delta P 2 upon delta delta 3, delta P 2 upon delta delta n, right. This is with respect to delta, and this side is delta delta 2, delta delta 3, delta delta n. The next one is delta V 2, delta V 3, delta V n, these are all changes in magnitude, right. And then delta P 2 upon delta V 2, delta P 2 upon delta V 3, delta P 2, delta V n, these are magnitude, but not telling again and again, understandable, right. Similarly, delta P 3 delta delta 2, delta P 3 delta delta 3, delta P 3 delta delta n. That means, when you take for delta P 2 all the derivative you are taking with respect to delta 2 delta 3 delta n with this, right. And when you take, and so it is delta P 2 upon delta 2, delta P 2 upon delta and so on, and this part will be delta P 2 delta V 2, delta P 2 delta V 3 and so on. Similarly, here delta P3 upon delta 2, delta P3 upon delta 3 and delta P3 upon delta n. Similarly, here delta P3 delta V2, delta P3 delta V3, delta V3 delta Vn, right. This way you will come up to nth term. Similarly, for Q also, delta Q2 upon delta 2, delta Q2 delta 3, delta Q2 delta n, here delta Q2 delta V2, voltage magnitude of course, delta Q2 delta V3, delta Q2 delta Vn, right. This way you can construct. So, this is actually partition, here it is 1 here, assuming that all the buses are PQ buses for this one, right. Later we will see PV bus. So, and this is delta 2, delta 3, delta n, and this is delta V2p, delta V3p, delta Vnp, these are all magnitude. So, this is equation actually 52, right. So, this equation, this part, this one actually, this equation is n minus 1 into n minus 1, because bus 1 is a slack bus. This partition, this matrix is n minus 1 into n minus 1. This is also n minus 1 into n minus 1. This is also n minus 1 into n minus 1. That means, as a whole, the dimension of the matrix is 2 into n minus 1 into 2 into n minus 1, right. So, that means, this equation 52, bus 1 is assumed slack bus. So, this equation can be written in general that delta P delta Q is equal to J1, J2, J3, J4 delta V, right. So, delta P is equal to, not writing here, and delta P is equal to delta P2, delta P3, delta Pn, this vector, and delta Q is equal to delta Q2, delta Q3, delta Qn, right, and J1 is equal to this matrix, right, that and delta J2 is equal to this matrix, J3 is equal to this one, and J4 is equal to this one, right. Now, generally what happen in transmission line power system, right, they have a very low R by X ratio, right, because R is less and reactance is high, right. So, for such system, real power mismatch delta P are less sensitive to changes in the voltage magnitude. That means, if you take the derivative delta P to delta V to this changes are your real power changes, this your not very voltage sensitive, right. Therefore, for real power mismatch delta P are less sensitive to changes in the voltage magnitude and are very sensitive to changes in the phase angle. I mean, these are significant, right, very sensitive in changes in phase angle, but not very sensitive with that this thing changes in this one voltage magnitude, right, with respect to that, right. So, in that case what we will do, this term will neglect, this matrix will neglect, right, only this one we will consider. Similarly, similarly the reactive power mismatch delta Q, the reactive power mismatch delta Q is less sensitive to changes in angle. So, this part, that reactive power changes is quite less sensitive to the changes in angle, but very sensitive to the changes in voltage magnitude. That means, this part and this part will drop, right. This matrix will not consider, but we will consider this one and this one, right. So, that means that this is my J1, this is J2, this is J3, this is J4. That means, that J2 and J3, that these are set to 0. So, these two things will not consider, but J1 and J4 will be considered, this is delta V, right, because this is we want decoupled, right, and that one, and if you consider this one, if you consider this one, this is coupled, right. So, that means, you can write delta P is equal to J1 delta and delta Q is equal to J4 delta V, magnitude delta V understandable, right. So, this is equation 54. So, that means, delta P is equal to J1 delta, this is equation 55, and delta Q is equal to J4 delta V, this is equation 56, right. Therefore, for voltage control buses, the voltage magnitudes are known, right. That means, if you have a voltage control bus, voltage magnitudes are known. Therefore, if m buses of the system are voltage control bus, J1 will be always of the order of n minus 1 into n minus 1, because this J1 matrix, this is your J1 matrix, this matrix actually, this matrix your J1, this is your J1 matrix and this matrix actually your J4, right. So, if in a PV bus, if you consider that in PV bus Q and delta, this your P and voltage magnitude known, Q and delta unknown, right. So, this will remain as a n minus 1 into n minus 1 matrix, this one, right. But when you have a PV bus, this thing, so in this case what will happen, suppose in general you have a n bus system and you have m number of PV buses, right. Then this J4, order of the J4 will become n minus 1 minus m into n minus 1 minus m, because voltage magnitude is known, right. So, in that here those wherever voltage wherever the buses where voltage magnitudes are known for PV bus, those delta V changes will not appear here, right. Similarly, here in this. So, that means that J4 J4 is the order of n minus 1 minus m into n minus 1 minus m, right. Suppose you have a 10 bus problem, then J1 will be 9 into 9 matrix, and suppose in 10 bus problem you have 3 your what you call 3 PV buses, then it will be 10 minus 1 minus 3, that means it will be 6 into 6, J4 will be 6 into 6, right, but this one will be 9 into 9, right. So, later we will see when we will consider PV bus, so we will take one example, right. So, now your what you call that the diagonal elements of J1. So, this is the J1 matrix. So, diagonal elements is delta P2 upon delta delta 2, delta P3 upon delta delta 3, delta Pn upon delta delta n. In general, delta Pi upon delta delta I, right. So, this way we have to first diagonal, then off diagonal elements, right. First diagonal, then off diagonal elements we have to obtain, right. Therefore, this is your, just hold on, this is your expression of Pi, right. So, this is your expression of Pi, right, this is expression of Pi. So, in this here you have to take the derivative now, right. So, what you will do that your first is you take del Pi upon delta delta I. If you take del Pi upon delta delta I, diagonal elements is k is equal to 1 to n, k not is equal to I. If you take the derivative one, it will be V I V k y I k, right. Cosine, if you take derivative minus, and with respect to minus delta, so another minus will come out. So, ultimately it will be your plus. So, it will be V I V k y I k sin theta I k minus delta I plus del k, but this summation symbol will be there. Now, question is that for your clarification, what you will do, that why this summation thing comes, right. So, what you can do is just for your this thing, just hold on, just for your understanding, right. For example, you take just hold on, you take this one, right, you take this equation, right. Let us for just for the purpose of your understanding, suppose n is equal to say 4, right. And this equation, this Pi equation, we can write like this, that Pi is equal to say k is equal to 1 to 4, right, then Vi, then Vk, then Yik, then cosine theta ik minus delta I plus delta k, and your what you call, this is the thing, right. So, k is equal to 1 to 4. Now, you expand, right. If you expand, then your say this is your Pi. Now, you have to expand for your same thing, say I is equal to, say my I is equal to 2, because bus 1 is a slack bus, say I is equal to 2. That means, my P2 will be is equal to k is equal to 1 to 4, right, then V2, then Vk, then Y2k, then cosine, then theta I is equal to 2 to k minus delta 2 plus delta k, right. Now, what you do, you expand this, you just I will show one, then you will know. So, now you expand this, right. If you expand this, then your P2 will become, right. So, it will become V2 and then V1, then Y21, right. Then cosine theta 21 minus delta 2 plus delta 1, right, then plus your V 2, then k is equal to 2. So, V 2 it will be V 2 square actually, right, V 2 into V 2, V 2 square anyway, then y 2 2 cosine theta 2 2 minus delta 2 plus delta 2. So, this delta 2 will be cancelled, right, then plus your V 2, then your V 3, then y 2 3, then cosine theta 2 3 minus delta 2 plus delta 3. This is the third, and we have taken one more 4. So, plus when k is equal to 4, V 2, then your V 4, then y 2 4, right, then cosine theta 2 4 minus delta 2 plus delta 4, right. This is the fourth term we have taken, but this is actually V 2 square, right. So, this delta 2 will be cancelled. Now, if you take derivative, say we are taking the derivative in general delta P 2 upon delta delta P I upon delta P I upon delta I, we are taking the derivative, right. Say they say it is diagonal. So, I is equal to 2, that means delta P 2 upon delta 2. To take the derivative of this equation with respect to your delta 2, right. If you take the derivative with respect to delta 2, you will find delta 2 is here. So, if you take this term, the derivative exists. Similarly, here it is independent of your this thing, second term, that V 2 square cosine theta 2 2, right. So, if I rewrite once again, right, it will be P 2 will be is equal to V 2 V 1 y 2 1 cosine theta 2 1 minus delta 2 plus delta 1, then plus this is V 2 into V 2. So, it is V 2 square, then y 2 2, then cosine theta 2 2, because delta 2 will be cancelled. Next term is V 2, then V 3, then y 2 3, then cosine theta 2 3 minus delta 2 plus delta 3, right. Then last term is V 2, then V 4, then y 2 4, then cosine your theta 2 4 minus delta 2 plus delta 4, right. That means this term, if when you take the derivative delta P 2 upon, when you take delta P 2 upon delta 2, this one will be there, and the derivative exists, delta 2 is here. This term no delta 2, it will be 0, but here also delta 2 is there, here also delta 2 is there, here also delta 2 is there. That means, if you take it is V 2 V 1 y 2 1, right. If you take minus, because of cosine minus and because of minus delta 2, another minus will come out. So, it will be plus. So, sine theta 2 1 minus delta 2 plus delta 1, right. This is the first term. Second term is 0, it is not there. Look, with respect to 2, but these 2 terms not there, right, plus V 2 V 3, then y 2 3, then here also sine theta 2 3 minus delta 2 plus delta 3, right. And last term V 2, then your V 4, then your y 2 4, right, then sine theta 2 4 minus delta 2 plus delta 4, right. So, all the 3 terms are there, only second term is not there, right, because this is that ith term I is equal to 2. So, it is independent of delta 2. So, this will vanish. So, this is 0, right. That means 3 terms are there. That is why when we take the derivative of this one, the diagonal one, right, diagonal one, it is V I V k y I k sine, because everywhere sine is there, right. So, magnitude V I V k y I k sine theta I k minus delta I plus delta k, k is equal to 1 to n, k not is equal to I, because when I is equal to 2, this term is independent of delta I. So, it will become 0, right. So, that is why that k not is equal to I, right. Although in the equation everything k is equal to 1 to n only, right, but this delta pi, that is diagonal element, is sum of all this thing, but k naught is equal to I, but with a sign multiplication. This is equation 57. Thank you. Again we are coming.